Thank you, and thank you for having me. I want to take the next 2 minutes to tell you a little bit more about some exciting things we're doing at Quantum Machines. So to frame the talk, right, step back, hopefully many of you heard yesterday, but Quantum Machines focuses on quantum control. I'll say a little bit more about that in a minute. But to frame the structure of the talk, I want to start with this paper. You can find the reference at the bottom. The title is How to Build a Quantum Supercomputer, Scaling Challenges and Opportunities. It's a paper we published together with many partners, as you can see here, ranging from large companies like HPE, Applied Materials, Synopsys, including many startups such as Colab and 1Qubit, as well as many academic and research institutions who partnered with us to write this paper. Now, the structure of the paper, and it's long, I don't expect everyone to have read the entire paper. This will give you the highlights here. The structure of the paper is to define some of the key challenges we expect to face in scaling out quantum computers, and then to start to lay out a plan of how can we address them. And so we use a map from very small qubit count at the bottom and doing initial proof of concepts into medium number of qubit count of roughly where we are today, and up to large qubit count and fault tolerance in the future. And on this map, we lay out many of the different problems we have to face. And these range from qubit fabrication to quantum algorithms, but I want to focus today on where does quantum control come into play in these problems, and how can we help specifically. So I've highlighted here a few of the places where quantum control in particular is relevant. Let me make the others disappear so that they pop. And then let's also gather them together into 3 distinct topics. The first topic is really about quantum control, orchestrating quantum sequences and scaling the control hardware and being able to scale to large qubit count. The second part is about doing real-time decoding and interface with the CPU and GPU, and this is around error correction. And then the third topic is about being able to do large-scale recalibration of your systems and being able to automate the calibrations. So let's start with the first piece. This is the bread and butter of what we do at Quantum Machines. So being able to scale out the control. Our flagship product is the OPX 1000. It is a quantum controller designed to scale. For those new to the space, a quantum controller is the box that sits between your computer and the actual QPU. It takes in the quantum program you've written and emits the actual precise pulses, in our case, microwave up to about 10 gigahertz, which you need to actually control the processor. It has leading specs. We've come by our booth to learn more about the details, but I want to stress that it is data center ready, it is certified, and it scales up to thousands of qubits easily as one large virtual machine. It has the highest channel density currently in the industry, and we're excited to push the boundaries even further. We're most proud about it and want to highlight some of the ways it's being used. So we have over 80 citations by our happy customers and users in top journals, and I want to highlight in particular 2 examples of where it's been used. One has been by the group at Caltech, which were able to do phase correction thanks to the real-time capabilities of the OPX. So what does real-time mean? Real-time means that you can actually take a response back from the QPU, you receive the message back into the OPX, you process it within the lifetime of your qubit, and then you can perform the next step. To show that in a little bit more detail, I want to also highlight some work done by the group at Google. So Google performed feed-forward operations using the OPX's mid-circuit measurement capabilities. Again, for those who might be less familiar, mid-circuit means that in the middle of your quantum circuit, you measure some of the qubits in your system, and then the feed-forward means that you're using the results of that measurement to decide what to do next. So as you can see in the standard circuit that they started with, if you break it apart, then you insert the value of the OPX to the middle where you can run some of these measurements. You do classical processing within the OPX, within the controller, and then you can do conditional operations based off of the calculations you just performed, all within the lifetime of your qubits. Switching gears to the second topic, to the topic of error correction and being able to do the interface with the GPU, or quantum orchestration, the latency and the timescales are really important. So to lay this out, if you have your QPU sitting at the bottom and then you have to go to the controller, which is the OPX, but you're doing error correction. You also need some sort of decoder, which is going to run the calculations of where are your errors and what do you need to do next. We've done quite a bit of research to define what are the required timescales. And so you'll see first at the quantum controller layer, you need to have ultra low latency between the QPU and the controller on the order of hundreds of nanoseconds. And this is something we already achieve with the OPX 1000. Then you need to have low latency between your controller and your decoder, this communication channel. And we calculated that it needs to be below the 10 microsecond limit. And then you need to do the decoding latency, the actual time it takes you to run the decoder on your additional platform needs to be roughly 10 microseconds. So the top scale, the 10 microseconds, is something we look to partner with, and it's a challenge to many in this room who are working on decoders and ways to implement that to continue to push the boundary, and we'd love to partner with you. I want to tell you a little bit more now about the middle piece and the low latency connection between the controller and the decoder. So this is something we're doing together with NVIDIA. We have a joint product, we call it the DGX Qauntum. The DGX Qauntum takes the OPX 1000 that we've been talking about until now and tightly couples it through a specialized network card you can see called the OP-NIC to a NVIDIA Grace Hopper server, so CPU and GPU. And we've been able to demonstrate a 4 microsecond round-trip latency from the OPX 1000 to the Grace Hopper and back. So we're beating the 10 microsecond number that we said is required, and this is still our alpha version. We expect to be able to iterate and to improve on this going forward. The entire system is programmable with through Qua, which is our programming language at Quantum Machines, but also through CUDA. And so you can use the CUDA piece to write on the GPU, and you can also now integrate everything to CUDA-Q as well. To give you an example, the first example we've done of actually using this combined product was to do some reinforcement learning to improve the calibration of a single qubit. And so it interleaved the QPU, the CPU, and the GPU all working together. We leveraged the 4 microsecond round-trip latency, and we're able to do this all seamlessly to really improve performance. So if you look at the bottom right with some data, we don't need to go too deep, but the point here is that what you're seeing is the learning model as it iterates and tries to find the answer. And so a good outcome is convergence. And so you can see at the beginning on the left side of the plot where first it's exploring, the model is exploring, then it starts to learn, and it starts a little high, but and then it goes a little low, and it eventually converges to an answer. Similarly, on the right, you see as it gets darker into the pink, then it means that the model is, we are going forward in iterations, and you can see that in the low iteration count, we are jumping around the space we can explore, and as we get to the pinks, the values start to converge. So in both cases, in the 1D plot and the 2D plot, we can see the model converging quickly, and this was all part of the integration between the Grace Hopper and the OPX 1000. To shift to the third topic, I want to tell you a little bit about calibrations. So first, I would say that calibrations are challenging always. Even at the small scales, it is difficult to do. It is something that typically requires a team of physicists to sit and actually calibrate your device. And the calibrations need to happen fairly frequently, which in itself poses a challenge to operating these quantum computers. So developing the tools for that is something that's really important to us. We have an open source framework we've just launched called Qualibrate, which makes it easy to do your calibrations using the OPX 1000 and using Qua as our framework. But I also want to tell you a little bit about other partnerships we're working on toward that goal. But let me first point out why is it a little bit challenging. In order to actually calibrate your system, you have to run multiple experiments. Each of the experiments the data needs to be saved, and in many cases there are interdependencies as you run through this graph. And so it's step after step you need to iterate on. Sometimes you get blocked, sometimes you have to step back in your graph, sometimes there are loops in the graph, etc. And so there's complication here. This is what we're trying to make easy for our users, for our customers. So I want to tell you a little bit also about some work we've done with partners toward this goal. So last summer, we were fortunate enough to have a Rigetti Novera 9-qubit device that we were able to make available at the Israeli Quantum Computing Center, which is a research center at the University of Tel Aviv that Quantum Machines is operating and co-funding with the Israeli government. We took advantage of having this device there and invited multiple partners and friends of Quantum Machines to come and show off what they could do on the system. So I want to highlight results by two of our companies that we work closely with, close partners of Quantum Machines, and what they've been able to achieve. First, Quantum Elements took the approach of going very deep. And I want to call out that this was a short amount of time. It was a challenge. It was a show what you can do. And everyone took a slightly different approach, which was really impressive and exciting. Quantum Elements went deep. They showed that they can really squeeze performance on a single qubit, and that they can perform also calibration of 2-qubit gates extremely well. So you can see, for example, at the top, in the top left, blue and orange is what you would want to see. The bottom line, the brownish line, is where you would have an error. And you can see first the green line is close to the brown, right? It shows you have some sort of coherent error. And then they were able to, through their software, improve from the top to the lower picture and really push the green up to be in line with the others and really suppress that coherent error. You could see at the bottom as well, they were able to implement 2-qubit gates. And I will say that both companies are here, so please come find them. If you cannot find them, come find us and we can introduce you. Second, I want to show some results from Cruise. Cruise took a slightly different approach. Rather than going deep on a single qubit and trying to really optimize performance there, they were able to demonstrate that they could calibrate all 9 qubits and all 2-qubit gates within a very reasonable amount of time. And so again, you can see some of the single qubit data at the top. You can see at the bottom the time of each of the steps that it took as part of this calibration, and they were able to do the entire calibration of the device in under 45 minutes. And again, for both of these, this is a demonstration of what is possible, and we expect to continue to push the boundaries with them and with many of our other partners and users in the coming months as we go forward. Finally, I want to tell you a little bit about another partnership we have, slightly unrelated to the other topic, but it's exciting because it's new and it hasn't been talked about a lot recently. We have a partnership together with Oxford Instruments and Oxford Quantum Circuits, where Oxford Instruments is now providing an entire package of their fridge with an Oxford Quantum Circuits Lucy generation 28-qubit superconducting qubit device, as well as the OPX 1000. It has been validated that the whole package works as one, and I think the key point here is that this is really geared toward education. It is a system where you own all the components. It's not a black box. You can take everything apart. You can swap everything out as you go, and we really view it as a tool optimized for those who are looking to be able to train a workforce on how to operate all the various different components, how to remove components, how to operate a system on your own. So it is intentionally not a black box managed system. It is intentionally an open stack model. And again, this brings us back to the many other partnerships we have, including the ones we've touched on today. We do, Quantum Machines, really believe that there is a future of open stack in the quantum computing space, just like it exists in the HPC space, where you are able to choose multiple different products from different vendors and assemble them together to create your own custom piece. So if it's an example of these three, if you then are adding software from the partners we talked about before, if you're adding DGX Quantum and products from NVIDIA, if you're then adding, hopefully later, the decoders through additional partners as those become more mature, et cetera, we really believe this will be a big part of the future going forward. So to wrap it up, there are many challenges ahead, but we think we have ways to tackle them. We are excited at Quantum Machines to contribute where we can and to work with partners across those which are out of our space. And we believe there's a lot of exciting work to happen. If you'd like to participate in that, please let us know. We'd be happy to have a chat, and you can find us at the booth in the main hall. With that, thank you for your time.